All right, how we doing, everybody? Doing good? All right, let's see. Let me just set this camera up a little bit. Come on, there we go. All right, so let's do a quick diagnostic. How is Dr. Morris's class? What are you guys talking about right now? You guys going over LTI systems? Okay. He didn't talk to you about what linear constant coefficient difference equations are, right? Or did he talk about that too? LCCDE. No? Just another word. Anyways, so everyone's understanding what do you call it? Your guys' assignment, let me see. Computer assignment 3 is due this Friday, right? Is that confirmed? All right. I'm saying this in the microphone. It is due this Friday midnight, right? All right, that's good. So that gives us breathing room, gives the TA breathing room, gives everyone breathing room. Okay, I think that was a necessary thing so that everyone's on track. Okay, so you guys can have tonight, tomorrow, and Friday to mingle around and talk about the assignment. Okay, I want to make sure you guys know the MATLAB. All right. Anyways, let's see. Here's our courses. Here's EE360, and then let me see. Computer assignment 3, all right? Did anyone look into this already? You guys already starting it, finishing it? You guys understand what the Fourier series is about? Do you guys know why we even use it? No? Yeah, I know. That's it's funny because I work under Dr. Steberud. He's our other signals professor, and we tend not to show the Fourier series until we show you the full fledged LTI systems, linear time invariant systems convolution, and what's his name? You will see it definitely in this class, but I'll just talk to you about why we use it. It's a simple little tool. Let me see. Where's my visualizer? So I'm going to go down to the bare basics. So every signal is going to have, what do you call it? I'm just going to do some wiggle here. Let's call it x of n, right? And let's just say, if I were to produce a tone like this, and it's got a, what do you call it? All right, let's make it pretty. There we go. Time t, right? Is that good? But then this can also relate, if I were to call it t naught, right? This can also relate to, what do you call it? 1 over f, right? F naught. I'm calling it F naught or F0 to represent the resonant or not resonant frequency, like the what do you call it? It's the fundamental frequency of this signal. Okay, so if I were to tell you there's a special little device or special little technique where instead of looking at signals like this in terms of time, or I just put time right here. I think so. Yeah, let's do that. We can observe these signals as a function of, let's just say, harmonics. I'll call it F. See that right there? Not F, just regular F. There we go. All right, and this right here is like some amplitude of X. Okay. Yeah, I'm gonna do this. It's bad annotation, but it's just to explain. Okay. So if I have this axis right here, right, from 0 to F, right? And this is F naught, right? Let's just call this, I'm just going to throw a number like 1 volt, right? 1, right? Where would this be on the scale? Right here, F naught, right? I'm just going to have the stem right here, right? That's what it's going to look like in terms of its frequency information, okay? Is that cool? So I'm going to show you another thing. If I were to do the following, let me just do another signal. If I were to add like something like this, like that kind of signal, right? And it's basically 2 times F naught, like that, right? And let's just say this is at 0.5 volts, right? What is this going to look like if I were to add these two together? Let me just do like the addition, right? You're probably going to get something that looks like this. It's a bad wave, but like something like that, right? the addition of two sine waves, right? With two different frequencies, okay? This is just going to look like this. 2f0, boom. Is that making sense? So if you were to put like a spectrometer and analyze this signal for its frequencies, you're going to see these two little stems right there, right? Is that cool? So that I'm not trying to get really deep into this. I'm just trying to say this is a special domain of DSP or signal analysis where you can take apart a signal and realize every signal. If you had a funny signal, like I don't know, if I drew like some funny signal like that right there, you can dissect all the information just by doing a Fourier series. And then if you wanted to, you can build some special filters like if I were to go to the following page 2, right? I'm trying to show you guys a basic thing. You will see it in your assignment, but we're not going to go that crazy, okay? But I want to make sure it's not a surprise for everyone, okay? So let's just say I have, let's see, I'm going to do a funny number right here. That's 0. This is f, okay? This right here is f0, 2f0, 3f0, and yeah, let's just go 4. Okay? So this first point, if I were to do like the Fourier transform or Fourier series of x of n, right? This first point is very important. This right here is your DC bias or your DC offset, okay? Offset. Okay? So basically, if there's a number here, like if I were to use the color orange, like that right there, like let's just say, yeah, 0.5 volts right there, right? Then your output is going to be, well, DC at 0.5 volts, right? Then you can start designing some cool waves. Like if I were to do the following. There you go. There you go. If I wanted this kind of frequency right here, maybe this right here, start doing some funny designs like this right here, right? Right? If you added all these frequencies, right, based off the fundamental frequency, frequency, right, you'll get something cool like, oh, well, I don't know how to explain it to you, but it's more like this. Here's this one right here at 1 volt, like this, like that, and then this is for f0, 2f0. If you were to draw like this, let's see, here is half right there, so this would be half. I'm just trying to show you guys an example of what's going on. If you added all this, you're going to get any picture. So I think there's like a cool video out there by some YouTuber where he was like, you can draw like Mozart, like Mozart's like portrait using a bunch of like sine waves. It's really, really cool. It's somewhere. No, so basically what they did was they took a whole bunch of sine waves and then like, let me see if they can find this video. YouTube. Drawing Mozart using sine waves. There we go. Was it that? It was one of these. I don't remember. Fourier series drawing. There we go. Yeah, I see. Yeah, someone drew this guy using a bunch of these waves, and it's a really cool video. Maybe I'll send it to you guys. And you see that right there? You just draw these bunch of sine waves. Here's the DC component, right? DC, that's your resonant or your, what do you call it? Your first frequency, right? Your fundamental, double the fundamental, triple the fundamental. And guess what? You can also have negative frequency. See? And then look, if you just change stuff like that, you see, this is the cool part of signal processing. You can do a lot of cool stuff with this. All right? Any questions about that? So I think this is the reason. And then you see that right there. You can build pictures based off a bunch of sine waves. All right? Using the not resonant frequency, the fundamental frequency. Is that cool with everybody? Yeah, you can definitely check. Oh, It's an advertisement. But anyways, if you want to check it out, what is a Fourier series, you can go get that information for yourself, okay? Anyways, let's go back to here. Oh, that's an answer for later. Anyways, so I'm just talking to you. Oh, yes.
I think that's the assignment for next week.
This one?
Yeah. There's one before that that's on difference equations on his website.
No way, really? I thought this was. Oh, wait, is this the wrong one? Come on. Okay, anyways. Convolution. Comp assignment 2 due 211, okay? Comp 3 due. Okay, let's check this. Was I checking the wrong assignment? Unless he updated it.
I don't know. They both say number 3 on the phone.
That's interesting. Anyways, let's get your money's worth, okay? I want to make sure you guys. But anyways, that's the what do you call it? The outcome of this course. You will understand signals and systems can be made up of a bunch of sine waves. Anyways, let's see. Computer assignment 3, LTI difference equations. Oh yeah, because I talked about this. So, anyways, statements. Print the screen to see growth. Boom, boom. Let's see. Nothing too bad. He gives you an answer right here, right? You know that this is the answer, right? Did he tell you about this? Or should I go over it again? I'll go over it again, no worries. Then filter function. Yeah, let me just refresh that. I could have sworn. Yeah, comp 3. Anyways, we're going to go over this one, but I gave you guys the discussion for next week. Okay, so the reason why I was thinking I should go over assignment 4 was because with the due date of it being Wednesday, that's why I was preparing for computer assignment 4, thinking it would be due. So, anyways, thank you guys. Thank you. But I'll go over computer assignment 3 because that's what everyone's going over. Let's see. These are your answers, kind of. Maybe I'll go over that. Let's see. Filter command. Consider the third order difference equation. Direct form 1, direct form 2. Okay. This is not a bad assignment. I remember last week I was talking about this is not a bad assignment, okay? So you guys want me to walk through step by step how to finish this? And then I want to talk about Fourier series, okay? So, direct form 1. Let me see. Let me go back over here. Stress. Anyways, click here. So, direct form run. Let's see. DF, direct form 1. Is that good? Anyways, remember, did you guys like that a little analogy I made with if I had two companies, feed forward, right, and feed back, right? Sounds pretty simple. Cool, right? And then I have my X right there. Here's my Y right there. Y of N, X of N, right? And then I'm just going to show you a little hint right here. If I were to dash this right here and treat this as H of N, right? Our impulse response, right? What is an impulse response? It's the response of a system due to an impulse. All right? So basically you're kicking the box with a delta function, right? And you just kick it and see what happens. What does it spit out, okay? I'll show you that step by step, okay? Anyways, first steps first. We got to make our feed forward. Everything goes forward, okay? Feed forward, right? Direct form 1, the easiest one, simple, right? So, let's do the following. If I were to create a node right there, right? Here's X of N, okay? And let's just do the most basic one, because I made an error the last time. There we go. There we go. Does that go with everybody? So C of N is equal to, I drew this a little wrong. Ignore that line. B0, okay? B0 x of n. Is that cool? Right? So how do I get this other one? Plus B1 x of n minus 1. How do I get this? Take your line, delay it, right? Is that cool? B1. Is that cool? And then dot, dot, dot until you get to your, let's just do D, let's just use N, okay, dn, nth delay, okay, for feed forward, okay? And then you have, let me do this, B of n, okay? Plus, or actually you don't need a plus right here, you just go all the way there, dot, 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 okay? Is that cool? Plus, dot, 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 plus Bn x of, no messy work, David. Plus, dot, 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 plus Bn x n minus n. Does that go with everybody? Easiest block to do. I'm going to give you another hint too. This right here is known as a finite, what do you call it? FIR, finite impulse response. Have you heard of that term? Yeah? Why is it finite? So when I throw water in here, right? If I kick the bucket, right? If I were to throw water right here, right? Delta function, right? It just goes straight through, right? And then if it goes down here, right? It goes straight through, right? It's finite, okay? So you're going to see this a lot, especially when you're doing linear filters for h of n. If he gives you like, oh, like h of n is equal to this, like, I don't know, like this, 0, 1, 2, like this. It's the most simplest filter, and it just does this right here, 0, 0, minus 1, 3 right there, right? This is the most simplest FIR filter. It is really simple, not too bad, okay? And maybe I'll give you another hint next week's assignment or computer assignment 4. One of your H responses is literally this. 1 minus 1. Here's 0, here's 1. That's your high pass filter. Okay? I'll show you that in the assignment, okay? Is that cool with everybody? Direct form 1, okay? And let's do direct form 2. Or not direct form 2, the other part of direct form 1, okay? DF1, okay? But for feedback path, okay? So I have this signal C of n, right? It's just coming in, okay? But I need to do something funny with it, okay? Here's my output, right? And I can just stop there, and this is the simplest FIR filter, right? No feedback, it's simple, makes us happy. But let's say we want to introduce some type of, delay, okay? And yes, I'm going to be on this team. Minus A1, okay? Plus. Is that good with everybody? Right? This right here is an infinite impulse response. Right? Why is it infinite? Because if I throw water in here, right? If it goes through here, right? This goes straight here, right? But there's a chance it can go down here, right? And then it can cycle back here. What if this gain is too high? You get to the point where maybe this water is a little too big, right? And then you start having this positive feedback loop, right? To the point where your thing blows up. Yeah. With these types of filters, things tend to kind of go out of control. But there's a big positive is that you can get some really, really clean signals using feedback theory, okay? You'll learn that a lot in your control theory class, where you can see that instead of having non-linearity FIR filters like this right here, you can get some really cool, stable, linear lines. Everything just fits perfectly because you have this line trying to argue saying, hey, I have a signal, right? Uncontrollable, right? But this weight right here can control whatever happens at the output or the input. Does that make sense? Anyways, if I were to continue this down like this, delay, right? And I think for this class, I don't think you guys are going to go any more higher than this. But if you do need to know, D, I'm going to call this one mth delay. Okay, and minus AM. Okay. Is that good with everybody? This is your second company, all right? Feedback company, all right? Is that good with everybody? So there's a reason why I did it like this, okay? And then let me just do this. Y of n is equal to, let's see, who wants to help me with this? Y of n, right, is equal to C of n, right? Right? Easy? I'm going to do minus right here, right? What does Y of n see? The minus A1, right? Delayed Y n minus 1. Is that good? Then I'm going to do minus A2. You see the pattern? Minus A of M. Y of n minus M. Is that cool with everybody? This is how you design these feedback paths, okay? So there's a reason why I did it. I did 2 different sheets of paper. So if I wanted to do direct form 1, right? Here's my feed forward company right here, right? If I just put this right there, right? You guys like that? Cool? This right here is your full direct form 1 block. Does that make sense? Now, remember how I said, well, I want a direct form 2, right? You can see where I'm going to lead with this now, right? Direct form 2, okay? You just do it like this. Feed back to the feed forward, right? Is that good with everybody? I'm going to show you the trick that I was trying to show you. See this right here? Like that. Here, treat this as your new X right here, your input. You're throwing everything going through here, and you see how it works, right? Right? I throw water here, right? And it goes through here. Oh, it cycles, right? Oh, no. But then look, it can go straight through, right? See, and then look, you have all these delays and all these cool paths. Sorry. Anyways, that's the easy way to show you direct form 2. Is that pretty cool? You guys like that little example? But no, I want to make sure you guys go home with a clean piece of paper, okay? So let's do it. So let me remember just looking back at what I drew, because I kind of liked it too. X of n plus, right? Then I need to go from there to all the way straight through. Okay. So if I were to draw this node here, right? And let me see. Should I go through the easy way or not? The intuitive way, or should I show you the shortcut way? Or both? Both? Okay, I'll show you both. Okay. Give you guys your money's worth. BO. And then, let's see, plus. There we go. Y of n. Does that go with everybody right there? So I'm going to show you the other way I was trying to show you, the easy way, kind of. D right there, right? Minus A1, right? And then arrow like this into here, right? D, right? Is that good? Minus A2, right? Is that good? We're doing the feed back, right? We're going back. Plus right there, right? Plus right there, right? Is that easy? Is that good with everybody right there? Are we following? Okay. What does Y of n see? It sees this BO, right? Times this input right there, right? Is that cool? But it also sees, well, this multiplied by this right here. Is that how I want to show you? Is that how I want to show you this circuit? Yeah, I guess that's how I want to implement this. But basically, this sees this, and then this right here is your entire feedback. Does that make sense with everybody? And then let me show you this other one. D right there, right? And then if I were to do B1 like this, plus D, B2 plus. Does that go with everybody? Direct form 2? So let me show you the other way, and this is why I don't kind of like this way, because it makes sense like this, but I'll show you. Here's part 1 or what do you call it? Number 1 or first way. Okay? So back in the days, companies would have to design this and this, right? Do you see these delays right here? What if I can tell you we can, like, these cost like $1 each, right? And you're building like 1,000 of these or 1,000,000 for your customers, right? We can save a lot of money if we just, share these two. Does that make sense? Did he go over that in class? Yes? Okay, so anyways, so that the grader knows, okay? Here's what I'm looking for. X of n, and B0, plus right there. You can just share it like this. Cool. A1 plus, and then B1 right there. Y of n. Does that make sense with everybody? And then there's something cool about this. Has he talked about state spaces in the class? No? All right, that's going to be a hint for later. I'm going to show you right now. And this is where I don't know if he's going to put this in an exam in the future. But do you notice how, like, it's weird that this is X of n, right? And this is, well, whatever this is right here, right? What's the name of this node? There's no name, right? So let's just say I'm going to call this one node, let's call it Q1 of n, right? All right? So this is introduction to like state spaces, where he says, okay, you have this signal Q1, right? Then you delay it, boom, it turns into Q1 of n, or Q1 n minus 1, right? But I don't want to talk too deep about that, okay? So I want to make sure you guys do your assignment, okay? So you can finish the rest of this, right? Okay? DF2, what was turning off? Second way. Good? So now let's attack your assignment right now, because I want to make sure you guys can go home happy. Getting this done. Anyways, let's see. Using a for loop, write a program to implement the direct form 1 block diagram. Oh, wow, he made your life a lot easier here. Okay, he's not asking for a lot. Dr. Stuart asked for direct form 1, direct form 2, and transpose direct form 2. So maybe Dr. Morris is really nice to you guys, okay? Because let me tell you this. How do I implement direct form 1? Let me show you. So I don't have to go over this piece of paper. Anyways. See all these equations I just created? So I have to first create my company 1, right? This company right here doesn't exist, okay? Boom. C of n, right, is equal to your first input with the gain, right, plus the next, boom. First part done, right? You have a node Cn, right? Or is he calling it C of n, or is he calling it something else? Q of n, W of n, right? And I'm just calling it this, okay, for consistency. C for consistency. C of n, right? Now you do your second line of code. You see? Direct form 1. Good? So, let's go over your assignment, and let me tell you now you're understanding, oh, he gave us a solution. What does this look like? That's your feedback, right? What does this look like? That C of n part, right? And then look, he just gives you the first case, okay? And does he tell you this is direct form 1? I wonder if he does. Okay, let me see. I don't think he did, but let me see what the assignment's asking for. You can use a for or a while loop, so he gives you freedom, okay? Let me see. Let's do it Dr. Morris's way. Use a for loop. Nope. Boom. Okay, I like this one right here. Are you guys copying and pasting these ones? Let's see if it works. Boom. Oh, I don't like that. Ooh. Anyways. Boom. Did anyone try this one? Anyways, I want to run this, see what he was trying to do. Okay, there we go. 15, 16, 17. Let's run it. Control Enter. What? Oh, space. What? Oh. You know what? Let's not copy paste. Anyways, let's call this class EE360 D. This lecture 4. So the first thing you're going to do is you're going to have your A. I like doing it like this: A0, A1, A2, and how far do we go down the assignment? Let's see. B0, B1, B2, A1, A2, A3. Okay, 3 delays. Okay. Let's see. A0, A1, A2. Nope. A1, A2, A1, A2, A3, B0, B1, B2. Okay. And then there's something he did, and I understand what he's trying to do here. A1, A2, A3. If you do it like this, your life kind of becomes a little easier with sorting. B0, B1, B2, okay. And then what numbers did he give us? 1, 25, and 1. I'm just going to put this on the side right here. Okay, there you go. A1 is 0.5, 0.1. Okay, wait, no. Yep. A3 is 0.2. Okay, B0 is 1. B1 is 0.25. B2 is 0.1. Cool? Anyways, did everyone get this part right here, right? Understood? So now, let's see. Let's not look at that. Let's go here. N is equal to, I'll give you a hint. Usually when you see these A1, A2, A3, right? What does this usually mean right here? We have like 3 delays, right? Let me just check. Hold up. A1, 2, 3. Yeah, 3 delays. 3 delays. Oh, why am I copying that? A0 is equal to 1. B0, B1, B2, B3. Okay, let's see is... Oh, wait, where am I copying this from? I'm copying the wrong part. No one's telling me. It's okay. Copy this, okay? Don't forget the minus. This one right here. Okay. A3. Don't forget the minus, but I'm just doing this because I know it's going to generate an error. B0 right here. Okay. 4. Okay. There you go. Come on. B2. There we go. And B3. So everyone got to this point, right? If you're sleeping, it's okay. It means you've understood what's going on. Anyways, 0. Oh, very tedious. There we go. Oh. Anyways, there's 3 delays, okay? So I'm going to go backwards in time, -3 right here, right? And then I'm going to go forward in time. He wants 51 outputs. I'll just put 51, okay? This is my time, okay? I'm going to do x, right? X, let's call it xa, okay? Is equal to the delta function, d0. But how do I define d0? d0 is equal to, you guys like this trick right here? N is equal to 0. Creating delta function. Is that good with everybody? All right. So that's our first signal. For I is equal to, let me see, this is the hardest part of the day. N, okay. Y, I'm going to do this funny thing right here. C of I is equal to, let's see, B1 dot times X of I. Is that good with everybody right there? Right? Is that what he did in the code too? Let me just check, because he does give you these answers. While, for, okay. Because this right here is the funny thing we got to play around with. I want to make sure everyone can go home understanding why we did this. Okay? Anyways, let's see. Let's see. B1 of I. What do you guys think about this format here? Is this good, or would you rather it be this? Does it matter? You like this one better? Okay, because I think I like it better too. B1 dot times X of I minus 1, okay? Plus B2, see now I can keep track of everything. X I minus 2 plus B3 dot times X I minus 3. Okay, is that good with everybody? And then we can do YI, okay? Is equal to CI, right? Right? Minus. Okay, now let's think about this, okay? Because this is where things can mess up really badly. Okay, let's look. Where's your assignment? Right here. Okay. He gives you weights. I'm going to assume you have to put the minus sign here, okay? Let me just check that one more time. Okay, yes, you have to put these minus signs, okay? Don't forget them unless your thing's going to blow up the other way. It's going to be positive feedback, and you're going to see a squiggly line, and it's just going to go like this, okay? Did someone witness that already? Good. Okay. Anyways, A1, oh, come on, A1 dot times YI minus 1, okay? Minus A2 dot times, I like using dot times because I like making sure everything's scalar, okay? I minus 2 minus A3 dot times YI minus 3. There we go. Is that cool with everybody? Okay, anyways, let me just get rid of all this right here. I want to do it from scratch. Now the hardest part is your time, okay? Making sure everything's on time. So let's see. I'm going from minus 3, right? But if I do I is equal to if I put 0 right here, right? If I make I 0, right? I is equal to 0, right? First off, this is going to start barking at you, okay? Then this is definitely going to bark at you because I with minus 1 is going to give you an error. So let's go to the worst error, which is these two signals, X I minus 3 and Y I minus 3. So what's the first thing I should do? Because this is not C++, we're not array index 0, we're using +1, right? So I'm going to do +1 right here, right? To account for that. Plus, I'm going to do the following. I teach my other DSP students, Dr. Stuber, to do this. Delay. Okay? Or my delay. How many delays do we have? 3? There's a reason why I teach it like this. Right? How many delays do we have? 3, right? So now when I is equal to, what's our delay? 3, right? So 3 plus 1 is 4. So when I is equal to 4, right? It's going to look at this one right here, right? That's good. Let's go here. 4 minus 3 is 1. We're good. Okay? That's the reason why I teach it like this, okay? Anyways, now the hardest part is to go to the end. Make sure we don't break the cycle at the end. So if I were to show you, it's going to have a 1, okay, plus a delay, plus, let's do length of x. I think that should work. We'll see. I spelled length wrong. There we go. Let's see if it barks at me. Figure 1. Stem n x. Is that what he wants you to do? What does he want you to show? Use the program to calculate the first, okay. Recall the out, okay, yep, impulse response, okay. Overlay the plots of the input and output using the stem, title, and subplot commands. The subplot should have part A and B. So A and B respectively. Wait. Okay. On the top row and C. Okay. He wants one exercise on one graph. Okay. So I think what he wants you to do. So this is going to be called name exercise 1 or 2 because that's the problem. Subplot 2, 2, 1. Okay. Let's do stem and x, right? Or xa, okay? And then I'm going to hold on stem and y. Let's do ya, okay? So I think another thing I want to teach you to everybody here is how to pre-allocate memory, okay? This is another important thing to know. So you can do the following. We don't have to do that there, but it's a good thing. It's good practice. XA, right? Zeros. Let me see. What do you call it? Length of n, right? Is that good? And then I'm going to keep it like this, okay? I like keeping it like that. Okay? Pre-allocate memory, okay? Is that good? And then I'm going to do YA, right? Copy paste this right here. Boom. Okay? So now everything's pre-allocated. We can start working with our signals. First thing I did was already just fill up this guy right here, okay? Is that cool? And then let's do this, YA. Let's see if this works. Hold off, legend. I'm going to do X of N. Y of N. There we go. Let's see. It did bark at me. Okay. Error. Unrecognized function or variable X. Oh. No one warned me. There we go. XA, XA, XA. YA, YA, and YA. Is that better? Let's run it. Unrecognized variable. Where? Oh, there it is. Items must not exceed 55. Okay. So our signal is 55 length. What is this right here? Let's evaluate. it's 59. So we're going from 4 to 59. 59 minus 4 is 55. It doesn't like that. So you know what I'm going to do? Get rid of that one. What? I think I know what it's barking at me, and I feel sad to show you this. Forgive me all. Let's see if this works. Okay. I don't think it likes it when you feed it that type of information. These are matrices. So I think it wants me to feed it a matrix like that. Beta what? Okay, this is 4, 1. Oh. Control Z, Control Z, Control Z, Control Z, Control Z, Control Z. There we go. 1I. There we go. Apologies for that, y'all. Let's see. There we go. Oh, there's one more thing we got to pre-allocate, everybody. Let's see. There's one more signal. C. What is C? It's our node. Okay. Let's pre-allocate this memory. Boom, boom. Good. Position 2 exceeds array indices. YA. Is anyone seeing the error? You know what? I'm going to do -1. See if that fixes it. What? YA. Let me check. Clear vars. Let's run this. So if I run this, okay? Run this down here. F9. Okay. So our signal is 55 length, okay? 55. That's our signal right there. Run it, okay? X of A. We want to start at 1 plus 4. So this is going to equal, let me do the number. 4, okay. So this is going to be 4, 3, 2, 1. Cool. And this right here is going to be, there we go. There's that. 4, 3, 2, 1. Let's index it. Okay, it doesn't like this point right here.
Is it because there's a space after the negative A2, or?
I don't think so. See, this is the headaches I have with MATLAB. 1I minus 3. Because if this right here is there, you know what? I'm gonna give it. Let's feed it that. No, it doesn't like that either. So what could be the problem? C is declared. Oh no! I see a problem. It's right here. So basically what happened was I kept creating too many rows. I should have did this. Length of n. There we go. MATLAB's painful. This should run. Bingo. Does that look like an impulse response? You like that? Now, let me just make it a little bigger. I'm going to do it color blue. And then line width 3, okay? And then I'm going to color this one red. You like that? That's a little too thick, sorry. Boom, boom. So I think this is what we're expecting to see, right? You kick the box, boom, response, right? I'll tell you a hint, engineers. There's a function you can look into. It's called help function. And let's just say you're a little, this is for those who really want to investigate this. You're like, man, I have to retype this over and over again. You can create a function that just does it all for you. Boom, you can get the assignment done in like 2 seconds. Anyways, what I'm trying to say is, if I wanted to do xb, right, is going to be equal to the unit step, right? Right? Okay, unit step. And then, let's see, delta. How do I make a unit step? Right here. Unit step u0 is equal to n has to be greater than or equal to 0, right? Easy. It's going to be painful to replace this all over here, right? Are you seeing what I'm saying? You can create a function. But I don't want to get into that, or should I? Nah, I want to talk about the filter thing. But anyways, let me just copy this. Paste this right here. Length of xb, okay? I'm going to call this one cb, okay? This is xb, xb, xb. Oh, don't mess up the naming conventions, because you will. I did it back when I was a freshman too, or a junior. That's what everyone's here. Okay, b and cb, okay? yb, okay? Okay, there we go.
In MATLAB, can you make a separate variable like a j or a k in the for loop, and then use that as a variable for like I minus j?
Oh, yes, you can do that too, where you're indexing like different types of functions, right? Yes, you can do that as well. So you can reuse the same, you can make 2 for loops, a for loop that goes through every equation and a for loop that does the actual program itself. So there are many ways of approaching this program. The point is, what I want to show you is this. How to make sure you guys do this right here too. XB, YB. What's the title? Title is unit step for this one right here. And this right here is the right there, title delta. What? Oh. I know what I did. I got rid of this one. Wait, CB. There we go. What? YB. Oh, okay. This is what I mean by pre-allocating stuff, okay? I'm going to do this again, okay? XB, YB, CB. Is that cool? Boom. You like that? Are you understanding what's going on right here? When I kick the box, right, I'm going to get an impulse response, right? It wiggles and sets. Like if I were to hit like this water bottle, if I were to teeter-totter like this, and you see how it wiggles and comes back to rest, right? That's an impulse. You hit something and it has a response. It wiggles like, woo, like that, right? A step response is, how do I say? It's like if I were to, I don't know, move this up like this, and you see how, like, I don't know, I'm trying to replicate something, but point is, it's like, two things about systems. How does it respond when you hit it, and how does it respond when you give it full VDD? All right, these are the 2 most important responses in signals and systems, okay? So you're going to be seeing this a lot in this curriculum, not just this course, but in every other future course in DSP. Does that make sense with everybody? And then for the filter function, you guys use it? You see how it's easier? Filter function is not that hard, right? Let me show you. Quick, easy one. Filter function. Okay? Let's take our same signal, XA, right? We already have that, right? That's the delta function. I'm going to create YA filter, right? It's going to be filter. What does it ask for? It needs your B's. He was thinking about y'all. He really cares. You have to have these arrays, okay? okay? I'm gonna do this for the filter functions, okay? B, A, and X of A. And then I'm gonna copy this right here. And this is where we're gonna end off right there. Or maybe I'll talk about, okay, exercise 3 was it filters. Okay, XA, YA, filter. Boom. Is that the same thing? It should be. You see, it's a lot more easier instead of coding all of this right here. It's just this. Cool? And then, okay, you can generate this, you can generate that, you can generate that. Calculate the error, you just subtract the 2, okay? Exercise 2A minus exercise 3A. And he said, basically he's saying, is it 0? Is the error 0? Is it perfect? And then explain what the system is doing to your signal. What is happening to the input and output? So can everyone explain to me what's happening to the input, right? Or if I hit the input right, it's a square, right? Or it's a VDD, right? 0 to 1 volt. I turn on, I flip the switch, right? RC circuit, right? And it settles, right? And it settles to 1 volt. Cool? That's how you're going to explain it. And then there's the sine waves, and I could show you that quickly. But is there any other questions, okay? And then we're all, yes?
Well, I forgot, like, are we supposed to, like, submit the code in, like, a PDF, like, to Word, or is that...
Okay, this is where we're going to talk. So, because I think we like the Word one, right? Is that easier for you?
Yeah, it's less like word file.
Yeah, because in the past we made them also submit the M code so you run it, right? But I think with this course it's a little more vigorous, and I'm okay with. So what you're gonna do is you can do this. Let me show you. Go to MATLAB, okay? You can either do it 2 ways. Mine's doesn't work. I don't know why. Go to Publish. Go to this little arrow right here. Can't zoom into it. You can either press this one or this one. If you press this one, I think it'll give you an HTML. But go here, Edit Publishing Options. Oh, it needs me to save it. EE 360D Lecture 3, okay? Or no, 4, okay? You can go down here, Output File Format. If you want to go straight into the PDF, you can. That's okay. But if you want to like tinker around to make sure it looks nice for Joanna, okay, you can go to Doc, boom, Publish. Let it do its thing, okay?
But, like, do you want separate code?
Oh no, the code's going to be included with when you publish it, right?
Oh,
I'll show you right here, okay, and then we're going to end off right there. Then let it do its thing. Let it do its thing. You can do the PDF route, and it does it all for you, but some people want to re-edit their assignments, which is okay. So now you see, okay, I forgot my name, okay? You can put your name by David. Now it's easy for you, okay? Pre-allocate memory. There's the code so that the grader can make sure, like, hey, everything's running. This is the important part, right? Do you like that graph? What do you think? Should they use, like, line with 1? Right? Yeah, let's try line with 1. The point is, can you understand this? Explain this? Yeah, maybe use like, because for demonstrations, because that's why because if I make it really big, okay? If I make it really big, this makes sense to make it line with 2 or line with 3. But for the piece of paper, it does ratio everything down. So do be careful about that, all right? Any questions? All right? Have a good day, everyone.